Hello everyone, in this video I want to talk about calculus, the notation that you use to do calculus, and some explanations of important things in calculus. Because a lot of the time, the way calculus is taught is that after they give you the one lesson about the first principles, where you've got the fx plus h minus fx over h, aside from that they don't really teach you anything about how the notation works or why it is the way it is. So key questions that I want to be answering in this video: what does dy over dx mean? And what does ligma, well, it's a ridiculous name for the integration symbol, but for reasons that will become clear later, including for shortness of saying it, that's why I'm gonna call it in this name. What does this dx mean? So firstly, the key thing to note is that the first reason that calculus was invented by Newton was because of the falling apple, because the apple is accelerating towards the earth. So surely at some point he reckoned that at any singular point of the apple there's got to be some velocity, even though it's always changing, which would be the differential of acceleration. And that's the reason we got calculus in the first place, to calculate distance and speed and acceleration and all that. Anyway, so if you look at a graph, I'm going to explain this one first because it introduces what this lowercase d means. You've got this graph here, and say it's a curve, and you want to find the gradient at a single point. Now, of course, normally the gradient is, you've got a straight line, and then you figure out how much across, how much up it goes, and this distance across, you call it, it's the change in x, or delta x, and this distance upwards is the change in y, or delta y. You might be more familiar calling this rise over run, but this obviously does not work for our curve because we want the size of this triangle to be infinitesimally small. Like, given the state of this triangle now, it's not an accurate gradient because it's too big to actually fit like perfectly to the curve. So it's not representative of what the real gradient is. But anyway, when you find the gradient of a straight line, you've of course got that the gradient m is delta y over delta x. Now, one thing to notice is that this delta, the symbol for delta, is a capital for the Greek letter delta, meaning change. And in fact, the lowercase of delta, it looks like this, which you may recognize as the logo of this channel. Anyway, this is our lowercase delta, and a capital delta here stands for any change which is not infinitely small. But of course, when you have the curve and you're looking at an infinitely small change here, an infinitely small change in x and change at y, an extremely small triangle from which you're calculating the gradient, then the small change in x that you're measuring and the small change in y that you're measuring, instead of this triangle for the uppercase delta, because it's a big change, since it's an infinitely small change, almost zero, like you can almost treat it as zero, since an infinitely small change is going to be the delta x, or rather this is the delta y and this is the delta x, because it's an infinitely small change in y over an infinitely small change in x. And of course you've got the gradient m of this curve at some x would be dy over dx. So that's basically why the gradient, or the differential, is called dy over dx, because of course it's a hassle to write out this lowercase delta, but anyway, because delta represents change, it was decided that a lowercase d would be used in order to represent an infinitely small change in some variable. So that's how you get dy over dx as opposed to delta y over delta x when the gaps you're measuring are larger. So dy by itself represents the infinitely small change in y on the triangle you're measuring at the point on the curve, and dx represents the infinitely small change in x that you're measuring at the point on the curve. And this is to some infinitely small scale. Like this triangle should be nothing because it's infinitely small, of course, but this just helps you visualize what the dy and dx actually mean. So of course, if you take dy over dx, since it's basically rise over run, but the rise is extremely small and the run is also extremely small, so you get a reasonably sized number. Like by reasonably sized number, I mean like not almost zero, like 6, 10, 12, something like that. So that's why it's dy over dx to represent the gradient. So hopefully this kind of makes sense for now. And of course, the thing that they teach you in the first principles is that you're changing x by some variable h, and you go from the level of fx to, which is here, to the level of fx plus h, which is here. And of course, this is because at this coordinate, we have some x, and at this coordinate we have some x plus h because the gap in between them is h, which is why you get these two different levels of fx and fx plus h. So your delta y would be fx plus h minus fx, of course, and your delta x is just going to be this minus this, or the h that we decided it would be. And what really you're doing here is when you make this so infinitely small, you're making h so infinitely small that delta becomes a lowercase d in both cases here to get the differential. And the way this is written out is as, like, you might have seen lim h to 0 somewhere. And what this basically means is that pretend h is almost 0, but like not really 0, so we can still do things like divide by h and stuff until we get rid of all the denominators of h, and then we make it 0, which is why you get something like lim h is 0 fx plus h minus fx over h, because this part is the delta y, which will go to dy when h becomes 0, and this part is the delta x, which will go to dx when h is 0. So the key thing to know that is that dy and dx by themselves are extremely infinitely small, and when you divide one by the other is only when you get back into the normal sort of range of numbers that you might expect from a differential. Alright, so I hope I cleared up what dy over dx is. Now we're going to look at what is the integral for dx. So the way integration originated was that basically you wanted to find the area under a graph, right? So originally, if you take physics, you might know that people's estimates of areas under graphs was just from taking a lot of rectangles underneath it, or trapeziums if you want to be more fancy about it. And what people thought was that, hey, it looks like the more rectangles you take, the more it'll actually be like the curve. Like, for example, if you have this curve here, and there's the axis, if you take infinitely small rectangles, they will be quite close to matching the shape of the curve. So obviously, if you can make the width of one rectangle go to 0, then you will get the area. So of course, if this is a graph of y against x, any width of the rectangle, we can call it a delta x, because we are multiplying, we are just moving slowly along the x-axis and adding up the areas of these rectangles. So the area would be the sum of at any point here, this would be our fx, and then multiplied by delta x. That's basically what the integral is looking at. It's looking at the sum of the area of these rectangles under here, where each rectangle is some fx. Here, 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 here is the height, and the same delta x is the base of the rectangle. And you might be realizing that this looks kind of similar to the integral notation that we have already, because here the width of the rectangle is some number delta x, and of course when you make that extremely small, when you take this to 0, it'll become a dx, which is how you get the sum of fx multiplied by dx, because you're taking this continuous sum from the end of a graph to the next, or your upper and lower bounds basically. And of course, instead of writing sum every single time, people just write the integral notation, which looks kind of like an s times fx dx, to represent when you're integrating a curve from a point to a point. Now, one thing that is yet to be cleared up is, why does dy over dx, when you integrate dy over dx, why do you go back to y? So the thing really that's happening there is that basically for integrating, say you have some function y is blah 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 x, and if you differentiate it, you get dy over dx. So if you integrate it, you integrate dy over dx with respect to dx, because it's really the height of the rectangles you're adding up is dy over dx, and the width of the rectangles is dx. So since dx is going to be the same number, you can kind of multiply them together, because this over dx cancels out with the dx, and you're just left with the continuous sum of dy. Now, if you're summing up all of the parts of dy, since d means it's the infinitely small changes in y, adding them all up together continuously will just get you to y, which is back where we started. And that's why if you integrate the differential, you'll get back to the original function. And the property of being able to differentiate and integrate a certain expression in different directions is called the fundamental theorem of calculus. Basically, the fact that dy over or like the integral of dy over dx respect to x is y. This is what calculus is based off. So hopefully I was able to make this notation for dy over dx and this symbol dx clearer for you guys. So to recap, dy over dx, the lowercase d was the way of naming an extremely small change in some variable. So as opposed to delta y over delta x, where the changes are reasonably sized, dy over dx is when the changes are infinitely small, as you would do when you were trying to calculate the gradient of a curve, which is why if you have the rise over run being the gradient of a straight line, the infinitely small rise over the infinitely small run is going to be the gradient of a point on a curve. And of course, this is the continuous sum of something with respect to all the dx's. So it's really just adding up these infinitely small width rectangles where the height is the height of the function, because normally you'd have some delta x where the height of this rectangle is fx and the width is delta x if you're going through this curve here. But if you make delta x smaller and smaller and smaller, it'll go to dx, which is why you get the notation for it being the sum of all the fx times dx ever. Or instead of sum, you get this integration symbol, fx dx. And that is essentially why this expression right here, this explanation right here, is why integration is the reverse of differentiation, which is the basis of a lot of what you will learn in the future. Or like the technique that to integrate something, you just anti-differentiate it. Alright, if you have any questions, please leave some in the comments, and I'll see you next time.